Welcome to part 1 of the vectors lecture. In this lecture we're going to look at what vectors are, how they can be represented both normally and on graphs, and also we'll look at unit vectors and simple ways of adding and subtracting vectors from each other. The first question to be asked is, what exactly are vectors? Well, they're mathematical objects that have magnitude and direction. They're also a very useful shorthand notation, as they're a compact way of describing lots of related information. We can draw vectors using an arrow, where the length of the arrow represents the size of the vector, and the direction of the arrow represents the direction in which it's pointing. So for example, we have vector A, B, C, and D all as completely different vectors. Note that when we label vectors, when written in typeface, we use a bold typeface to represent the vector, and when handwriting, we underline the vector just to emphasize that it is a vector. Drawing vectors as an arrow with a certain size and in a certain direction leads on to the notion that if another arrow has the same size and points in the same direction, it must be identical. For example, vector A here is identical to this vector, and this vector. They are identical, so each is really the same as the original vector A. However, this vector, although it points in the same direction, is not of the same magnitude, so is not identical to vector A. Similarly, this vector has the same size as vector A, but points in a different direction, so it isn't identical to vector A either. Defining a vector, such as vector A here, leads nicely onto the idea that a vector which has the same size but points in the opposite direction must really be the negative of the original vector. So vector B is the negative of vector A, and so are vectors C and D. In addition, the fact that vectors B, C and D have the same size and point in the same direction means that they must themselves be identical. In other words, B equals C, which equals D. In order to give a little more structure to a particular vector, it is useful to represent it on a graph. So using vector A, we can draw a graph around it. I've arranged the axes here so that the base of the vector is located at point 2, 2, and the head of the arrow at point 7, 5. A vector can now be described as being the difference in the x-coordinates and the difference in the y-coordinates. So vector A is 5 units long in the positive x direction and 3 units in the positive y direction. In other words, A is equal to 5x plus 3y. This way of representing vectors as graphical objects is so common that a special terminology has been developed. Rather than use an x and y, it is often more convenient to use what are called Cartesian unit vectors. Cartesian is the name given to this sort of coordinate system used on a graph such as this, and a unit vector is just a vector with a length of exactly 1, and I shall have more to say about them shortly. However, this means we can define a vector, such as vector A here, as the sum of two groups of unit vectors. Unit vectors in the x direction are given the special symbol I, and unit vectors in the y direction are given the symbol j. In this example, vector A is 5 units in the x direction and 3 in the y direction. So in terms of the unit vectors I and j, the vector A can be described as A is equal to 5i plus 3j. Since a negative vector is the same size as the original but in the opposite directions, it follows that we can describe a negative vector simply by reversing the signs of the components of the original vector. So for vector A is equal to 5i plus 3j, vector minus A must be equal to minus 5i minus 3j. In the last slide, we looked at describing vectors as the sum of unit vectors I and j. In other words, we can describe a vector as the sum of two sets of vectors. One set is the number of unit vectors in the x direction, and the other as the number of unit vectors in the y direction. In essence, we're just adding the two sets of unit vectors. That adding process can be extended so that we can add together any two vectors. For example, if we have a vector A equal to 5i plus 3j and vector B as I minus 5j, the sum of the two, A plus B, can be found. Graphically, we place the tail of vector B onto the head of vector A. It is easy then to see that the result of adding these two vectors is 6i and minus 2j. To obtain these numbers without the hassle of actually drawing the vectors on the graph, we can add together the respective I and j components to obtain the same result. In general, with two vectors A is equal to a1i plus a2j and B equal to b1i plus b2j, A plus B is equal to a1 plus b1i plus a2 plus b2j. Vector subtraction is similar to that of vector addition. Remember that a negative vector is a vector in the opposite direction, and to describe a negative vector in terms of unit vectors, we simply reverse the signs of the I and j components. To subtract vector b from A, we add vector A to the negative of vector b. In other words, A minus b is equal to A plus minus b, which gives the component form A minus b is equal to a1 minus b1 I plus a2 minus b2 j. We can use the familiar vector A to determine how we can find the size of a vector. In component form, vector A is described as 5i plus 3j. We can see that graphically these two components form a right-angled triangle with a hypotenuse equal to the vector A. The length of A can therefore be found using Pythagoras. The length of A is normally called the magnitude or modulus of A and is denoted using the modulus symbol. The magnitude of A is then the square root of 5 squared plus 3 squared, which is the square root of 34. In general, given a vector A made up of components a1i and a2j, the magnitude of A is found as the vector sum of these components. In other words, the square root of a1 squared plus a2 squared. Although we shall not cover it further in this lecture, this is easily extended into 3 or even more dimensions. In 3 dimensions, a vector A comprises 3 components, a1i, a2j and a3k. The magnitude A is the vector sum of these components. We already know that a unit vector is a vector of length 1. So far though, we have only used unit vectors in either the x or y directions, the I and j unit vectors. This allowed us to describe any vector in terms of its magnitude in the I direction and magnitude in the j direction. Unit vectors are much more general than this, however, and can be found in any direction. It is often useful to be able to describe a unit vector in the direction of another vector. For example, using vector A, the unit vector in the direction of A is a vector exactly 1 unit long but in the direction of A. Unit vectors are given yet another special symbol using a caret or hat above the vector to show that it is a unit vector. This means that vector A can also be described as A is equal to the magnitude of A times A hat, or as the unit vector A hat multiplied by a scale factor equal to the magnitude of that vector. For the vector A equal to 5i plus 3j, we know that the magnitude of A is root 34, or about 5.8. So A equals approximately 5.8 times A hat. This then allows us to determine a unit vector as the vector divided by its magnitude, i.e. A hat equals A divided by the magnitude of A. So for vector A is equal to 5i plus 3j, a unit vector in the direction of A hat, is then equal to 5 over root 34i plus 3 over root 34j, which is approximately equal to 0.86i plus 0.51j. To summarise, given a vector A made up of components a1i plus a2j, a unit vector in the direction of a hat, is defined as a divided by the magnitude of a. This gives a hat equal to a1 divided by the magnitude of a, I, plus a2 divided by the magnitude of a, j. This is the end of Vectors Part 1. Here we have explored how vectors can be added and subtracted, and also discovered how to use unit vectors. In Part 2, we'll describe ways in which vectors can be multiplied together. Thank you for watching.